Welcome to this presentation, Transition to AUTOSAR, a change in multiple dimensions. My name is Andreas Horn. I'm a senior consultant at Vector Consulting Services. And before we start digging into this topic, what does it mean, a transition to AUTOSAR? Let me first introduce to you who is Vector Consulting Services. So Vector Consulting Services is part of the Vector Group, and although we are a quite small part of the Vector Group, we are supporting clients worldwide in different industries like automotive, aerospace, IT finance, digital transformation, medical, and transport in the 4 areas that we have designated with the 4 T's. So the first T, transformation, so everything that has to do with introduction of new processes, ASPICE, agile, or just for efficiency. The topic of trust, the second T, everything that has to do with safety and cybersecurity, and not only talking about the standard, but also the engineering that is behind all this. So doing safety analysis, safety architectures, and verification, pen testing, supplier audits. The 30, the technology, so everything that is directly related to a technology like AUTOSAR. So this presentation is part of this part of our portfolio. And we are also dealing in this area with different tools and how to best use them, integrate them into your processes, like, for example, Prevision. And the last T, the training, where we teach and coach everything that we do, that we have learned from all these projects that we have done over the world. And here in this presentation, we talk about AUTOSAR, so technology topic. And so let's see how this technology evolves, why AUTOSAR has gained such an importance today and will have even more tomorrow. So let's take first a look at the new vehicle architectures that are evolving currently. So currently we are in the area of domain fusion, so that informations from different domains is combined, and the next vehicle architectures will be what we call vehicle fusion, and also then connection to cloud computers. So we normally see this 3-layer approach where everything that has to do with the basic functionality of the vehicle, the foundation layer, that is where, let's say, the low-level action takes place. So all these sensors, the actuators, they are all part of this lower level. And the information and functionality that is realized in this foundation layer is then integrated into the high-performance layer that is realized using high-performance computers or clusters. This is the layer that really realizes afterwards this fusion over the vehicle. And on top of this, we have the connectivity layer with also the gateway and also infotainment, instrument cluster, head unit. This is then part of this layer. And this is also the layer that establishes the connection to the outside world, to other devices, to the backbone, to the cloud. So this is where this takes place. And at the heart of this, we need operation systems on different levels. And this is where AUTOSAR comes into the picture. And we see it's not limited to one platform. So here we see both platforms are required for the foundation layer. This is the domain of the classic platform, where we have more signal-based communication using CAN bus, LIN bus, and so on. And as soon as we come into this high performance layer with Ethernet connections, with high speed, then we are in the area of the adaptive platform. And so AUTOSAR is at the heart of these new vehicle architectures. And now let's take a look at what does this mean for the development processes that are used to develop the components, the software for such architectures. So first, let's take a look at this classical V model with requirements engineering as a starting point in the top left corner, then over architectural design, then you do detailed design, unit construction, then you start down there with the verification and go on over integration and testing to the qualification tests. This is sometimes referred to as an implementation-centric view because the bottom is what really creates the value here. Also, when we introduce AUTOSAR, this is an essential part of the development, but other parts gain more importance. And especially the integration becomes far more important, and this also then puts more emphasis on the architecture. And based on the architecture, we have to configure all the AUTOSAR stack, and then we can integrate the developed software components into this architecture. And so AUTOSAR enforces an architecture-centered development. And so this is what really makes the initial difference when you really introduce AUTOSAR. And we as consultants have seen many AUTOSAR projects run into problems. They do not always run smoothly. They struggle and fail in the end. And we as consultants are often called, when these projects are about to fail, to save the day, to save the projects. And over all these task force projects, we have made the experience that many AUTOSAR introductions fail for really rather obvious reasons, because the transition to AUTOSAR is just reduced to introducing a new technology, but this is really not the case. A successful AUTOSAR migration is a change project with the 3 dimensions of process, technology, and competences. And with this, having said, we have built upon this one of our consulting products we have called the AUTOSAR Health Check, with especially deals with this situation of introducing AUTOSAR into a new development environment. And there we look into these different areas of technology, competencies, and process, and check also your current environment. So if you plan to introduce AUTOSAR, we see what you are doing, what kind of products you have, what are your architectures that you have in place, what capabilities do you have, and then based on vector experience and industry best practice, we provide useful information hints. We outline the improvements that are really relevant for your successful transformation, your successful transition to AUTOSAR. And so this presentation wants to give you an insight into what are the major issues that there are when introducing AUTOSAR. And we put it down to 4 typical assumptions that will be the red line through this presentation. So the first one will be, there is no need for a dedicated architecture. AUTOSAR is an architecture itself. The second assumption, I can take over my legacy code. AUTOSAR can consume any kind of software. The third one, AUTOSAR is ready to use out of the box. And the fourth one, in adaptive, everything is a service. And along these four points, the following sections will show what is maybe correct and what is maybe wrong about these assumptions. So starting with assumption number 1, there is no need for a dedicated architecture. AUTOSAR is an architecture itself. And already with this assumption, we start with the weakest spot, let's say, in the transition to AUTOSAR. If we take a look again at this V cycle that shows us the AUTOSAR development stages, it's really this point where we meet the most challenges and where we see most often the greatest gaps. So it starts with a lack of architecture coherence, because AUTOSAR is rather ignorant to surrounding system architecture. Then we have insufficient interface agreements. Major architectural gaps are observed due to not defining robust and stable interfaces. We have the illusion of a transferable software architecture due to AUTOSAR framework and good AUTOSAR products. So insufficient or no specific architectural activities, no specific documentation of the architecture. Basically, you only rely on the AUTOSAR tools and artifacts. You have no dedicated architecture, so architectural drivers are not determined, leading to unspecific and unfocused architectures. A systematic evaluation of an architecture is not possible. Design principles and patterns are not utilized. Design decisions are not made explicit. You have missing competences. Capabilities of the software architects lag behind actual needs. And you have unbalanced quality requirements. Trade-off analysis and scenario evaluation is rarely done, yielding in performance, safety, and security problems. But where does this come from that this area is so weak? So the first point is that before it was not so important. You could always fix this missing architecture on implementation level. And second comes of these well-known pictures, I would say, from AUTOSAR, where we see structure. We see the deployment of this AUTOSAR stack of these different layers to the controllers, to the microcontrollers. And by this, we see already part of an architecture. We see structure. But architecture is more than just deployment, than just structure. It is also behavior. So you always have to define these two. And when we talk about behavior, then we also talk about requirements, demanding functionalities, and constraints. So everything that really defines what the system has to achieve in the end. And this is why we call them the architectural drivers. And these quality requirements and constraints, they have to be explicitly developed together with the requirements for the functionalities, because the architecture is really determined significantly by these requirements and constraints. So this is the first point where we want to attack. These three topics are, let's say, the outcome of the same process of the requirements elicitation, because functional requirements, quality requirements, and constraints are all by themselves requirements, different types of requirements. And so if you systematically do this elicitation of requirements, you also develop quality requirements and constraints. This can be done, for example, using this quality model of the ISO 25010 that is structured in characteristics, which are these famous ILITs for the qualities like usability and maintainability, and functional stability for the functional requirements. And then based on these characteristics, the ISO standard defines sub-characteristics that then help you to address these more specific topics, for example, for performance, to address timing behavior, resource utilization, capacities, to address these details by quality requirements. And so these are afterwards really the defining factors for your architecture and also for the selection of your architecture, because many standards ask you to do an evaluation of architecture alternatives that in the end you do not do the same as you have always done. You also then evaluate alternatives. And this can then be done using these quality requirements and constraints. You can do an evaluation then of your architecture, you can do an assessment of your architecture, and you can do this trade-off analysis. And in this trade-off analysis, you take these quality characteristics, you prioritize them, and then you see how do these architectural drivers influence each other? Are they supporting each other? Are they contradicting? Are they neutral to each other? And then you can adapt your architecture based on these architectural drivers that you have identified. Our best practice on architectural drivers, first step is to limit the number of these drivers. The more you have, the more they can contradict and the less they contribute in the end. So limit it really to 3 to 7 characteristics. If necessary, perform multiple iterations. Only a few drivers enable the development of a specific architecture. The most important part is then to deal with the contradictions between these different drivers. Then elaborate specific drivers, make them really actionable and meaningful for the developers, communicate them to all stakeholders, communicate which characteristics have been covered and which not. And these architectural drivers should also be verifiable, analyzable to assure the compliance early. If you do an evaluation that you can see, I have fulfilled this driver, I've met this driver. The architectural drivers are in the end the only artifact to really analyze and document contradicting aspects of your architecture. So this for the drivers. The second part that really defines your architecture are the concepts. This is the box that you see up here in this architectural picture. Concepts are more generic than the drivers. The drivers are derived from your requirements, so based on the functionality, based on the properties that your system must exhibit to realize the functionality. These concepts are more generic, that the architecture in the end has certain properties. For example, these modern EE architectures, they are made for extendability, that it can be extended, that they are flexible in the end, also that they can be reused. And so these are then principles, patterns that are applied to these architectures. For example, modularization is one tactic that you can apply here to achieve this extendability. And then you meet these patterns and principles like separation of concern, that you only have a single responsibility, that you have interface segregation, and principles like open-closed. And these tactics on modularization, they also depend on each other. For example, the open-closed principle that you can read here is more effective if the other three principles are also applied. Now, coming more specifically to AUTOSAR itself, what are the characteristics and properties of AUTOSAR? So AUTOSAR has been designed for serviceability over the entire product lifecycle. It has been designed for flexibility, so abstraction of hardware from software, making the development more flexible. It is a shift from development activities from implementation to configuration, so configurability, and to be able to reuse functions across vehicle networks and across OEM boundaries, so reusability as one objective of AUTOSAR. And if we take a look at the AUTOSAR architecture itself, it is a multi-layered architecture that also applies the principle of information hiding. So just to put this here in this context. And such layered architectures follow additional principles like the backcall principle, that a top layer should only depend on lower layers, but not the inverse. the skip call principle, so each layer should depend only on the layer located immediately below it, so that you don't skip layers in between. Cyclic call principle, cycles of dependencies between layers should not exist because they make a set of layers monolithic and inseparable. These principles can then also be analyzed. So this is then also part of the architecture analysis, that you dig into your architecture and then come to a picture like this, where you can then clearly see, do you have really kept all these principles? Have you followed all these different principles? Have you skipped maybe layers? Do you have cyclic dependencies? Do you have backcalls and so on? So these violations of these principles, they can lead to unprotected access. They can lead to unused code. Here in this picture, for example, you see the onboard device abstraction is not used at all by the architecture, so it's really unused. And also to possible vulnerabilities, because these interfaces and these layers are there for a reason. So better use them. So coming to the second assumption, I can take over my legacy code. AUTOSAR can consume any kind of software. So when we talk about code, we talk about the implementation and the detailed design and unit construction. So at the lower left corner of this development V. And here we need the software architectural design as input, and based on this, we develop the detailed design and the unit construction. And here we meet typically the challenge of violations of AUTOSAR conventions and inconsistencies of architecture with implementation, so that the architecture definition is not followed and that the principles are ignored, bypassed. So, but before we dig deeper into what it means to do this development of software components in the context of AUTOSAR, let's take a look at what is really the intention of AUTOSAR concerning this development. So the idea of AUTOSAR is to be able to separate concerns and specialize on core competences. So if we take a look at such a normal ECU, we have a controller, we have the basic software, the RTE, we have the software components that afterwards realize the functionality. And so the underlying vehicle architecture is developed by the OEM because he knows his vehicle, he knows what is already in the car, so he is responsible for this layer. Then the applications running on these architectures, they are developed by the companies with the best system knowledge. So classical tier 1 business, or in the meantime, many OEMs are also active in these areas. And then the AUTOSAR components, according to the standards, they are developed by the companies with the best automotive software know-how. So tier 2 area, classical tier 2 area. And so these are just the characteristics of AUTOSAR, the objectives, what they really have in mind. And so the idea is really to follow the standard in order to enable this distributed development to make it also efficient. And this means that you have to really stick to the standard, to the principles of AUTOSAR, to the components, use them as intended to unleash the full potential of this AUTOSAR project, process, components, and methodology. And so if you do not follow this, these are potential sources of issues afterwards. normally it's really quite easy to not be AUTOSAR compliant. It starts with cutting corners. So you have software components that communicate directly with each other. So no need to go over the RTE. It's easier if I directly include and talk to other modules. But this leads to violation of principles, and this limits the portability afterwards. These components always have to be installed together as they have been created. So this creates a monolithic structure. This is not in the means of AUTOSAR. Then another potential source of issues is the skipping of layers. So not just following the RTE to communicate, but also to skip interfaces to directly access, for example, ECU abstraction layer, not going over the service layer. So directly accessing components. Again, this is a violation of principles. Defined specifications while bypassed, reducing the portability, maintainability, and also quality. These stacks are there for a reason. Service using ECU abstraction, using microcontroller abstraction. There is a reason behind all this. And so bypassing this is not in the intention of AUTOSAR. Using complex device drivers instead of standard components can be justified if it is for performance reason. If it is a very special application, then you can use the CDD instead of standard components. And sometimes it's not done for performance, but just because it takes really knowledge and experience to use the basic software stack as intended. So it can also be just to avoid digging too deep into AUTOSAR. But this again then limits the portability and it eliminates also reusability because it is just a special implementation. It's no longer portable to other AUTOSAR stacks. Reusing legacy code can sometimes be a good idea, especially when it is a very complex algorithm and you're not sure if you can really rebuild it. But always remember that with the taking over of functionality, you also take over insufficiencies. They are also then transferred to new functions. And unreflected reuse, so just taking the code as is into a new architecture, this may then also lead to the introduction of vulnerabilities into new architectures. And the last point, implicitly changing the architecture. If you are in an implementation-centric development, this is common practice to adapt the implementation to its needs and not to cycle back to the architecture. So additional components are used, other components are used. Maybe it wasn't mentioned in the architecture, but I can do it in the implementation level. And the worst thing is to not communicate such changes. And so this, in the end, also leads to incompatibilities and increased integration efforts. To show you how this can look like, one picture out of one of our projects where we did an architecture review. So this was the architecture like it was documented, and this is the architecture like it was implemented. And there you can already see more components have been used, other components have been used, and some components have also been directly accessed, skipping the layers in between. And when we talk about quality of the code, which is one intention of AUTOSAR to increase the quality of software, we also have to talk about the other properties that define what is quality, what are the inherent requirements that the system has to fulfill. And then we quickly arrive in these areas of safety, security, and availability with all these different standards that influence these areas and that also define these areas. And in many of them, you also find requirements to apply coding strategies like defensive coding. You have to apply coding principles, design principles for software units, and so on. So This is another argument, let's say, to not reuse legacy code unreflected, to always consider usage of the components of the stack as intended, or to re-engineer your source code. Because when we talk about these quality metrics, there's always the question, can we measure quality? And the most common set of metrics here are the HIS metrics that already give you a good indication of where are the blind spots, let's say, of your implementation. Is it comprehensible? How about the verification effort? How about properties like coupling or cohesion when we talk about functional safety? So this already gives you an indicator, how good is your code? Where do you have to maybe start again? What is maybe still good enough? Because violation of these metrics implies risk of additional costs for verification, update, or maintenance, and so on. So many things can be derived from this. So, but this is just to measure quality as a whole. When we go deeper into these standards, as already mentioned, you also have principles for coding, principles for designing your software units, and you also have industry best practice like anti-patterns, patterns to be avoided. The result can then be to apply coding rules, coding guidelines like MISRA that addresses many of these methods required by the ISO standard, ISO 26262 for functional safety. And the bottom just shows you one example how you can then identify the hot spots. That's why this is called also a heat map of your source code with the highest violation density. So this then helps you to identify the weak spots where you really would have to investigate, where you really would have to start reworking your source code to improve the quality of your system. Coming to the third assumption, AUTOSAR is ready to use out of the box. So the first thing we have to say here, AUTOSAR is not an operating system like macOS or Microsoft Windows or any Linux distribution. You cannot just install it on a system and then it will run. So let's take first again a look at this process picture where we are now. So now we'll focus on this middle part, because it's when we talk about AUTOSAR, you always have in mind the tools, you have in mind the methodology, the process that apparently comes with this tool chain. And let's now see what can go wrong there. And this configuration and integration step that we're now taking a look at, this relies on the inputs from the architectural design and the unit verification. This is where the two ways meet again, the two paths where they come together again. So all the pieces, the architectural design and the unit design, they now have to match. And this is also why we meet here again the severe quality issues that we have already seen with relation to the architectural design. You have a lack of measurable quality requirements, violation of AUTOSAR conventions. The intended integrity of the system is not achieved, and you have severe delays and rework during integration due to not following the AUTOSAR principles. So as mentioned, when we talk about AUTOSAR, you always have this workflow where you have your software component description, and then you map these software components to ECUs, you do an extract of your system description, and then you do the configuration of your ECU, you have the RTE, and then everything is fine. This looks easy, straightforward, it's tool supported from the beginning, but if we take a closer look, for example, just at the last step where everything comes together, it really becomes apparent that we are not dealing just with one flow, but you see the software components on top that come from the software detail design and unit construction. You have the ECU configuration description with the RTE config, the OS config. You have the basic software modules. And so all these topics flow together here over the compiler. You link libraries to it. So many pieces that have to really perfectly match in the end to build an AUTOSAR compliant stack. A vector offers a tool chain for this process. So here we see such a tool chain built on tools like Prevision, Canoe, DaVinci Developer, DaVinci Configurator, also the possibility to integrate model-based implementation tools. And you see all these different artifacts, all these different work products, the system description, the component description, the ECU system description, the extracts. All this has to fit in the end that you get really an ECU binary in the end. And there is even more files if we take a closer look, for example, at the Configurator Pro or the DaVinci Developer. So all these have to fit together. So it's not just having the tools, it's also about having the tool chain. But when we talk about tool chain, a tool chain is more than just the tools. So the sequence in which they are aligned, so the chain is basically a process. And this is in many cases under-specified, let's say, or underestimate. So here we see such a tool chain from architecture to the final binary file. And typical questions that you have when you see such a tool chain, yeah, it looks nice, but ARXML, this AUTOSAR XML file is just a container. So if you have data flowing in ARXML and an ARXML file is flowing out of this tool, what content is created where, changed where, needed where? So really think of content, not container. You have tools that receive data from multiple sources. How is the consistency, correctness, and completeness checked and assured between all these tools and between all this data? And then data is stored in multiple locations. Where is the master? Where's the single source of truth for which information? Then you see also milestones or stages here. Think in stages. Where in the tool chain is a consistent and complete data state? Where is it achieved? Where are the baselines managed? So tying in with configuration management. And also, where do requirements come from? Where are verification cases stored? How is the linking? So it's not just about building the executable. It has to tie in to your complete development process. And to give you one example from one project that we have, in many cases, as mentioned, we are called for support in such situations where you have an escalation, where where the companies, the OEMs themselves, all the suppliers have found out, we run into problems, and we run into problems regularly, and so we have to do something about it. And so we identify the root cause, if they are process related or tool related, and then we come up with an implementation strategy. And more tools is not always the solution. It's rarely the solution. You need above all methodology and competence. So you see the complete solution consists in the beginning of a manual checklist, then the development of suitable rule checkers, so partial automation, and then only in the end try to put it together into one consistent development tool chain, development process, that these problems are avoided, detected, mitigated. So this is always these 3 stages of fire prevention that we apply here. We have the first stage, which is the single task automation, where we run checkers, for example, manually to detect inconsistencies. Then we do batch automation, not manual execution, but batch automation. And then we try to put it into the whole tool chain, that it is automatically checked. And these automatic checks, when you talk about this, then you always talk about automation of integration, automation of build, and the trend in the automotive software development industry is currently continuous integration. And it's not just once continuous automation, continuous integration. You have even staged continuous integration. You have even staged continuous integration in the automotive EE business. And there's a big stimulus due to cybersecurity and changing business models. Having it once every 3 months, that's not enough. You need shorter cycles. And this is realized and using these continuous integration platforms and tool chains, where you have a reduced delivery time from weeks to hours. You make one change and then you can just restart the whole chain and all the tests, everything is executed, and then you have a new build at hand. This includes also reporting, and you have to handle all these reports also. So talking about the 4th assumption, in adaptive, everything is a service. So the most topics you have seen so far, although I used in many cases pictures from AutoSAR Classic, it's not limited to Classic. But now let's take a dedicated look at AutoSAR Adaptive and to find out if this assumption is true. Let's take a look at what are the differences between Classic and Adaptive. And then you see, okay, on the left-hand side, AutoSAR Classic, it is based on OSEC. All the AutoSAR modules are completely specified. It is developed in C. The whole stack is compiled and linked in one piece. The applications share single address space. You can use an MPU. It is optimized for signal-based communication. So for CAN, FlexRay, so really these traditional automotive bus systems. And the configuration is compiled into the binary. You can no longer change it afterwards. On the other hand side, AutoSAR Adaptive is an operating system based on POSIX. It has less modules. Only the API is really specified, so there's a higher flexibility here. It is developed in C++. The applications are separately installable. The applications use their own virtual address space. So memory management unit is then essential here. And you have the focus on service-oriented communication based on Ethernet. So we talked about the convergence of IT and EE, and the network of the IT business is Ethernet. And so also this network technology is now also coming more and more into vehicle architectures, because you need it, because it's far more flexible. You have higher data rates. So there's no really a way around Ethernet. And the configuration is loaded from manifest files. And this is also done during runtime. So which application runs when is highly dynamic in AutoSAR Adaptive. But coming back to the assumption that everything is a service, let's take a look at what is a service. A service is the encapsulation of subfunctions, of existing subfunctions, new functions to form services. these generated services are made available to all functions, can be internal and external, and the services are used on subscription concept using standard interfaces, and no discrete connections are established between components. So while we have a more classic function on the left side with this red connection between two functions, so this would be having a deep impact on the architecture. Maybe you would have to completely rebuild this architecture there to realize this red connection. These service-oriented architectures are far more flexible. They have the function, they have a service broker, and they have the services. Now, what do these three parts really do in this service-oriented architecture? So now let's take a closer look at these three. We have the service provider, which is the service itself. It is self-contained. It has a well-defined and published interface as in form of a contract, and it is platform independent. So where the service is not important. And it publishes to the service broker. On the other hand side, you have the service consumer, the application that connects to these services at runtime, and in order to do so, it asks the service broker, it uses the service broker to find the services, the service providers, and then the service broker provides the information necessary that the consumer can interact with the provider. And so they have then this direct interaction. And these service-oriented architectures, these enable dynamic extendability. So these services are really what makes this AUTOSAR adaptive. And it's not just this flexibility to connect them at runtime. There are also possibilities to extend this, the functionality, the services, the functions over time, over the lifetime of the vehicle. And this is done using updates and basically OTA, the over-the-air updates. And so services may change over time. Their availability may change over lifetime. Services can have changing response time. This is one thing to consider when we deal with services, and they can be implemented or provided from outside of the vehicle. So let us take a look at a typical use case. Here we have the cloud, and from this server that is in place to do these OTA updates, a service is updated. So maybe it is now then more secure, or it offers additional safety features, or it has more to offer even. This is one use case. Services and functions can be added dynamically. And as mentioned, the service broker does not care where the service is. As soon as it's published, its information, all the functions could also use services that are external to the vehicle. So what can we do now with these services? They are really an essential part of these new EE architectures, because they allow to make available vehicle functions to different consumers. A very simple use case is infotainment, where you can connect to the vehicle, and then you have direct access between the vehicle and the telephone on infotainment features, so you can then establish enhanced functionality on this top layer. But this stays on if we take a look at this multi-layered vehicle architecture, this stays on a very high level. When we talk about other features, we can dig deeper, starting with phone as a key. So we are accessing then locking features. They may not be that deep, but when we talk about features that use the light as service, let's say trailer light check. So this is one feature you are outside of your vehicle, you have connected a trailer to your vehicle, you're standing behind the vehicle, you connect with your smartphone to the vehicle, and then you can activate the light check, and then you see if the brake lights, the turn indicators and so on are correctly connected and working at the trailer. So this increases, it's not just only comfort, but it also eases then the installation and makes the connection even more easy. And remote parking, so you step outside of your vehicle and then you activate remote parking. So not just self-contained, but also talking about the vehicle connecting to a server that is then remote controlling the vehicle. So this can also be remote parking, or summoning that you are in a place and then you say to your car, come and pick me up. And then the vehicle is activated and picks you up. So really the services are essential for future connectivity features. And these services do not have just an impact on the functionality, but they also have an impact on your design process. And so here we see such a design workflow for a service-oriented architecture. While for AUTOSAR Classic, you started with a definition of your signals. Now you start with the definition of your service, because this service interface, the definition and the binding, this is really essential for what you can afterwards realize in your architecture. Then you have the software design with virtual function bus and so on. You have the switched network design. You have the deployment of service provider and service consumer to the architecture. So then it's quite similar to the classic approach, where you map then software and hardware together. And then you make a communication design, signal routing, data mapping, socket communication, and some IP. Many is not specific to adaptive, but some IP, this is then the protocol used for these services. And so this has to be configured. So and that brings us to the summary and outlook. First, let's wrap up concerning these 4 assumptions that have guided us through this presentation. The architecture, legacy code, out of the box, and service. At least for one of them, we can say it is mostly true. And this is the 4th one. So AUTOSAR Adaptive is built as a service-oriented architecture. So at the heart, this is true. Even though this is not the only challenge that comes with AUTOSAR Adaptive. For the other assumptions, there is no need for a dedicated architecture. This is definitely false. The contrary is true. You have to have a dedicated architecture. AUTOSAR enforces an architecture-centric development, so you need architecture. Concerning legacy code, AUTOSAR can consume any kind of software. This may be true, but that you take this as a guiding principle, let's say, for an AUTOSAR development, this is definitely wrong. This contradicts with AUTOSAR principles like the quality and reusability. And the third one, AUTOSAR is ready to use out of the box. It is a quite comprehensive solution with the AUTOSAR stack and all the tools that go with it, but it is not ready to use out of the box. I think this has become sufficiently clear. So in the end, don't underestimate the challenge of a transition to AUTOSAR. Act in time. And it will not stay on this level. Let's take a short look in what will come concerning AUTOSAR. As you have seen in this architecture picture, Classic and AUTOSAR, Classic platform and Adaptive platform, they will not exclude each other, but they will complement each other. So you have to find efficient workflows to address both platforms at a time. So processes that deal at the same time with the adaptive software design and the classic software design. And also concerning these platforms, the last word is not said. These platforms do further evolve. For example, for the AUTOSAR Classic platform, there is the flexibility concept that has just been published and that is being rolled out now. We also have projects running that use this concept that introduces clusters to make the development and integration independent from each other, to make the allocation and deployment on architectures more easy. And also concerning other operating systems, with connectivity comes the need to also communicate with mobile devices that have other operating systems, for example, Android. So Android has to be integrated into the AUTOSAR environment. And also coexistence is one topic of these future vehicle architectures. So not only having controllers that fully run adaptive, but having then microcontrollers, high performance controllers that use hypervisors that are capable to run multiple operating systems next to each other, like a safety operating system, a Linux or others. And all this in combination then with the classic micro processors that run classic microsar. So these are then the challenges of tomorrow, which we can also already see coming. So our message is here to really act in time and use the AutoSAR health check to be ready to deal with all of these challenges, not only dealing with the technology, but also deal with the competences and the process, and to do all this in time that you avoid cost-intensive rework, that you successfully introduce AutoSAR and transition to AutoSAR. Thank you for your attention.